So today I'll be talking about one of my research. So I'm interesting a lot on basketball and NBA analysis. And my idea was to create some typologies of player based on their shooting start. And so my one of the questions I was looking at was, is Stephen Curry really a guard? So if you are looking on the NBA.com website, you'll see this kind of data. So you can have the short chart for every player for the last, I don't know, maybe 15 last years, something like that. To be honest, I focus myself on the last 5 years. And so for each player, you have all the missed and made shot for every they were taken during the different games. So as you see, you have like here the short chart for Curry and James. And so you can have like different view of shooting shot for different type of player. So Stephen Curry is currently well classified as a guard, and so he shot a lot of three-pointer, and LeBron James is a forward, and he shot from like close to the basket. And so my idea was to define a density surface on the court, and so something that looked like that. So I estimate the probability density function for each player during these 5 years to shoot on different part of the basket, and I split up the two densities between the missed and made shots. And so, as you see here, LeBron James shot a lot of three-pointer, but he also missed a lot of three-pointer. And so that's why his density is really, his made shots density is really focused very close to the basket, as opposed to Stephen Curry, where the density is higher behind the 2 point line. And so after doing that, the idea was to say, okay, can we find a typology of the player where the densities look alike? So to do so, I'll briefly mention the mathematical method to do that. So it's based on the Karen-Lab decomposition, and the idea of this decomposition is that we can represent each densities as a linear combination of some coefficients time a basis of function, and this basis of function is based on the covariance function of your data. So in my case here, the data are the different densities. And then the coefficients are just the projection of my data onto the basis of function. And one of the difficulties here is that I have two-dimensional surfaces. I have two-dimensional. I have surfaces, and even bigger than that, I have vectors of surfaces, and I had to find a way to compute the covariance for this data. And the thing is, it's very difficult to estimate for four-dimensional function. And so the idea was to replace this estimation by computing what we call the Gram matrix, which is a matrix defined as the inner product between the observation, and this inner product is very easy to compute in that case, because it's just an integral between the data. And then you can show that what we call the eigenvectors of the Gram matrix are the same, are related to the eigenfunction of the covariance function. And so what I've got from that, I choose to keep four basis function, which are shown here. So each of them represent a different amount of variance within my data, and each of them are related to the densities of the player. And what we have to remind here is that the all of the functions are related to the mean function. So to interpret all this figure is that you have to compute the difference between this function and the mean. So if the color is red, is that it's above the mean, and if it's blue, it's below the mean. And then you can sum up everything, and then you have the density for the player. So the first eigenfunction is related to the difference between players that shot very, very close to the basket and players that are 3-point shooters. The second eigenfunction are related to, make a difference between players that shot inside the 3-point line and the ones that shot outside the 3-point line. And you can do the same thing for the third and fourth eigenfunction, but I won't detail it here. And so now we can look at the coefficient of the decomposition for each player, and so you get something like that. So on the graph here, you have the first coefficient for the different player in the NBA. And so if you are on the right side of the graph, so like Curry, it means that you have a higher proportion of 3-pointers than the players that are on the left of the graph. That who are like players that are more focusing on the shots near the basket. And so I can do that for every function that I got. So the second one, you see that Embiid is a player. Well, he didn't shot far from the basket, so he will have a very large, quite a large coefficient for this function. And so on and so forth. So here the third scored are mostly very, very close to zero, so there are not big difference between the player for this basis functions. And finally, the last score, and you see here that Curry is very far from the other, so it's really related to the fact that he shot a lot of 3-pointer and also in the direction of the basket and not in the wings. So now I can look at the decomposition for each player. So here I represent each of the basis function multiplied by the scores, and you can have something like that for each player. So what you see here is that, as a reminder, it's really compared to the mean function. So the mean density short for each player. So if it's red, the player will tend to have more densities, so more shots in this area. And if it's blue, it tends to have less shot in this area. So Curry shot a lot more than the average player of 3-pointers. He shot less inside the 3-point line. For the third function, it's basically zero, so it's like the average player. And for the fourth one, he really shot in the middle of the court and way less on the wings. And one of the things that I found funny is Chris Paul. So this player has very particular shooting types, in the sense that he shoots a lot right the elbow, and that's the only player that do that. Well, that's the only player that I was able to find in my data set that do that, and so his decomposition is very strange compared to the other player. And I finished by saying that I've done some clustering. So very, very briefly, I choose to do a K-Medoid clustering algorithm. So I select five players to start my algorithm. Why I choose to cluster my data in 5 groups, just because there are 5 players for each team on the court at every moment of the game. And so the idea is to assign each player to the nearest centroid, to the nearest player, based on some Euclidean distance. And so we recompute the medoids, and then we do that again and again until the algorithm converge. And so I found this result. So these are the 5 most representative players of each of my clusters. I should have ordered them by how many, by densities, but let's keep it that way. So the first cluster is players that shot some 3-pointer, but make most of the shots close to the basket. The second cluster are the players that shot a lot more from a lot more of 3-pointer. The cluster 3 are players that just shot very, very close to the basket, so basically the centers. Cluster 4s are players that shot a lot from everywhere. And finally, cluster 5 represent players that shot kind of a 3-pointer and also missed a lot. I will finish by comparing my clusterings with the actual NBA clusters. Well, I call NBA clusters the actual position of the player, so guard, forward, forward center, and center. So that's the actual typologies of players. And I see that I did not find much correspondence between the two, except maybe for the center groups, especially in that case on the right panel. So I did two K-Medoid algorithm, one with equal weights for each component, and one with components, weighted components. So the weights are defined with the variance that are found in my decomposition. And you'll see that the guard are very split into the different groups I found. And my explanation is that I only have data related to shoots, and the guard position is much more than just shooting, so it could also be, well, it could be improved with more data, like the pass data, defense, and so on. So that's really something that I would like to emphasize, that I just consider the shots data, and that's not something that um, should be taken as a definite truth or whatever. Like I taking a lot of uh, well, I don't know how to say that, but a lot of things to be careful of when analyzing this data. And as my time is done, I will just conclude by this picture of Stephen Curry. So I start by asking the question: is Stephen Curry is really a god? And my point is that, to be honest, I don't really mind. It's still very enjoyable to watch him play, so I'll be fine with that. And this particular pictures picture is terrible for me because I'm French and this picture has been taken for the final Olympics. And when he did that sign, we lost, and I was very very sad in front of my television. Thank you for listening, and I'd be happy to answer any question.